Hi. So in today's cooking class, we are going to prepare ketones. In the last video, we have prepared aldehydes, but now we will be preparing. You are in the kitchen. You want to know the ingredients. What are the steps? What are the supporting agents we need? Like that, we are going to prepare or cook ketones today in this video. So we know the aldehydes. So first we should know what we are going to prepare, right? So for aldehydes, this is a carbon atom. Here is a double bond with oxygen. On one arm, we can say, on one side, we can say there is an alkyl group, and we have on one side H. So there should be one H or one hydrogen with the carbonyl carbon. Other also can have H because at least, right? So these are called aldehydes. Have a clear distinction between aldehydes and ketones. So here the ketones is we have carbon, we have double bond oxygen, but in one arm we have an alkyl group, and in other arm we also have an alkyl group. So there is no hydrogen in this case. If hydrogen is there, it will be called aldehyde. If both arms are having an alkyl group, we will call it ketones. So that is what spelling is Ketones, ketones. We will call them ketones. So this is the end product we are going to get in every reaction or every preparation method which we are going to learn today. So what was our first substrate in aldehyde? Acyl chloride. The same we are having here. The shortcut, right? So we can remember like that. So we will be preparing ketone with the acyl chloride again for the ketones also. But yes, the reagent will change. So let me have acyl chloride here. This is the acyl chloride. Okay, chloride is this. So this I have. Okay, and now I'll be adding that with my reagent. So what I want, see, this is acyl chloride. I don't want this Cl. What if we get another R here? So then our ketone is prepared. Think like that. So we need a R. So our reagent will be R, don't worry. But the complete reagent will be, the complete molecule is R2CD. What is this? This is a metal, cadmium. And what is this? 2-alkyl group. And the name of that will be dialkyl cadmium. Make sense? Yeah. So this is cadmium. And focus on this word, mium, cadmium. Have you heard it before? Sodium, right? So they are all metals. Again, potassium. Yeah. So these are all metals. They are all electropositive. Electropositive. So this is for just your for information. So there is a metal carbon bond here. R is alkyl group, right? A carbon. So we have a metal bond here with a non-metal. Carbon is a non-metal. We will discuss it later. So let's have this reaction. What will happen? What will happen here? We will get a ketone. So how? Let's say R, C, double bond O, C, and the Cl will be gone. This R will get attached here. And now in both arms, I am having alkyl group. So this carbon carbon having both sides, the alkyl group, this is a ketone. We have prepared it. Great. And what is the side product here? Side product will be cadmium is here and chlorine is here. And they will mix up and give us cadmium chloride. I think you can't see this part. So I'll just shift it to right like that. Yeah. Now you can see. Yeah. CdCl2. So this is the ketone we have prepared. Now let's revise what has happened. So this is our acyl chloride. We have reacted it with dialkyl cadmium. That is a reagent which is bringing the change. Instead of Cl, R from this dialkyl cadmium is getting attached, and that's how we are getting ketone. And then the side product we are getting cadmium chloride. Now to simplify something here, first thing is to balance the equation. See that there are two chlorines here, and here I have only one chlorine. Like only one molecule will have one chlorine of acyl chloride. So I will just multiply it by 2 so that it balances. What else I can do? There is one confusion here. See this carbon. So this R has come from dialkyl cadmium. What about this R? This was already there, right? But now here I'm not able to distinguish between them. It looks like both R has come from this, right? It looks like both R's are coming from dialkyl cadmium group, but that's not the case. So how to differentiate that? To differentiate that, what we do is we'll put a dash here on top of alkyl group of acyl chloride. Put a dash here so that when the reaction happens, we'll put a dash here also. So now we can distinguish which R or which alkyl group is coming from which molecule. So this clearly now is coming from dialkyl cadmium because there is no dash, right? So this was got attached from dialkyl cadmium. And what about this? This was already there in our acyl chloride. So to differentiate between different alkyl groups, which molecules it is, we are using this dash. So don't get confused. This is just for our simplicity and understanding. So now let's understand the mechanism, how things are happening in slow motion. What is the action? So let's understand that very, very clearly. So our story starts with this, our reagent. So it's a metal non-metal bond, right? So it is a bond between R2 is nothing but carbon, right? So carbon and a metal, cadmium, right? So this our bond, this cadmium is a metal and this carbon is non-metal. And remember, when there is a bond between metal and non-metal, they are highly polar bonds. So our story starts when this breaks during the reaction. So I'm putting this line here so that you understand where these electrons will go. A single bond between two electrons, like they are shared. So carbon will take this electron also onto this. So what will it become? It will become negative. So one of the R has become negative. Its carbon has negative charge. Now what it can do? It will do two things. First thing is it will do nucleophilic addition. Why? It is negative, right? So it needs a nucleus, a positive charge. And do we have that? Yes, we have it here. So it will attack. So let's say one of the R of this dialkyl cadmium attacks this carbon. What happens? So let me draw this. So it was just sitting idle. It never thought somebody will attack, but it knows that this is positive center, so it will attack. A nucleophile will attack here, so it will try to establish a bond here. I want a bond with this, so this carbon, or I can say now the alkyl group, right? This alkyl group, R negative, is getting and trying to establish a bond here. But here is the confusion, right? The carbon can only have four bonds. So one, two, three, four, five. Fifth bond you are trying to make? No. Then we have to get rid of one of the bond. So who will do the sacrifice? The oxygen will take its bond back. And if it is pulling the electron onto itself, so it will become negative. So we will get intermediate product like that. So this will get attached, R negative to this, and R is getting attached here, and Cl here. And now we have O single bond. See now, single bond because one of the bond is taken up. So this will become O negative. Getting the bond broke here with one of the alkyl group and carbon became negative, so it became nucleophilic. It wants a nucleophile. It saw in acyl chloride's carbon that I can add it here, I can establish a bond here. And because we don't cannot have five bonds, carbon can have only four bonds, so one of the bond is taken back with oxygen. Oxygen said, okay, I will take my electron back, and it has become negative. So what I have done here will be called nucleophilic addition. But you know that the story is not ended here. We don't want this chlorine, right? This is fine. I want a double bond here and I want chlorine to be removed. And that is what the next step happens. When this kind of bond is established, this oxygen finds a way, okay, tries to establish its double bond back here. And doing so, this chlorine it takes now, see the two electrons, it takes now this electron and got eliminated. Okay, so there's a word, eliminated, right? So this reaction, which I'm going to do now, that will be the elimination of chlorine negative. So what I will get after this, so what I will get, the chlorine Cl negative will be separated and I will get R, C, this bond will be established again, double bond O, that's what we wanted in our ketone. So our ketone is ready, but the chlorine negative is eliminated. So this reaction which we did, this one to this one, this will be called elimination of chlorine. Elimination. Oh, I have to take care of the spellings. Elimination. Yeah. So nucleophilic addition happens and then elimination of chlorine happens. And if you are feeling sad about, what this chlorine will do, it got eliminated because this guy attacked, don't worry about it. We have his friend, right? Which one? C, which was separated. When carbon took negative, it became positive and Cl is also negative. So he will say, okay, let's be friends. So this will become cadmium chloride. So this chlorine will attach to the cadmium, which was left with the bond. Everything, a happy ending. And that's how, let's go to our first equation. See, so that is what is happening here. This bond is getting cut, then nucleophilic addition is happening here. This bond is taken back here. Chlorine is then got eliminated. This oxygen again established the double bond, and this chlorine get eliminated and attached with this cadmium positive, electropositive, and cadmium chloride is formed. And here we are getting ketone. So that is a mechanism for you for this reaction. So let's go toward the second preparation method of ketone. In aldehyde, we did the same thing with the acyl chloride, and the second was starting with N-nitrile, right? Nitrogen. So the same thing will happen. I'm going to prepare my ketone with a nitrile. That will be my substrate. It is like this, right? Carbon triple bond N. So let's see the reaction. So the reaction will be something like that. We will have CH3, CH2, carbon triple bond N. This is my substrate. Okay, so these are two carbons, right? So I can say ethyl group is attached with this carbon, right? Nitrile group. Okay, now I will add my reagent here, which will have a phenyl group C6H5. It's called phenyl group, and it is bonded with MgBr, magnesium bromide. That is my reagent here. So remember again, a metal has come into the picture. In the previous one, it was cadmium. Here it is magnesium, Em. The same thing will happen. It is electropositive. It is a metal. Carbon will take its bond, a negative electron. It will take into it and becomes negative and attack here. We will do this reaction. We'll have a supporting agent like baking soda we use in kitchen. We will use ether as our solvent. So it will happen in the presence of that. So ether will work as a solvent. And now what we'll get? The CH3, CH2, carbon one bond will be broken. So only two will remain. At this side, because now four bonds can be made, this phenyl group will get attached. C6H5 will get attached. And this MgBr will be getting attached to this nitrogen. Okay. And now our final product is not ready. So this cooking method needs two steps. The first thing was used ether solvent, prepare this. And now what I need? First thing, I want to break this. I want a lysis of that. Lysis means to break. And what I need is, if I put just double bond oxygen here, where I can bring oxygen from O, from H2O. So I need to do something which has a name called hydrolysis. Hydrolysis. So that is our friend here for the next step. So, and we denote it like H3O positive. And this H3O positive means we are doing hydrolysis in acidic medium. We will discuss this in later videos. So what hydrolysis, lysis means break, H2O means hydro. So the lysis will happen. This bond, double bond, nitrogen will be broken. And instead of that, O from H2O will get attached here. So we will get our final product, CH3, CH2. We got the oxygen from hydrolysis, right? And this got separated. So only C6H5 is remaining here. And if you can see, a carbonyl group having both sides, one side alkyl group, one side has aryl group. So this is our ketone prepared. But what we need to understand is how it is happening in the slow motion. So let's see that. Okay, so let's understand in slow motion what is happening. So here is our substrate CH3, CH2, carbon triple bond N, and we have this phenyl group attached with magnesium bromide, which is our reagent here. And what will be the name of it? It will be phenyl magnesium bromide. Okay, so the name, let me write it here. It is phenyl magnesium bromide. Okay, so what will happen here? See, here is a metal which is bonding with carbon, which is a non-metal. So again, the same thing which happened with the cadmium in the previous reaction. So the metal non-metal bonds are highly polar. And let's see what happens. So also I will show this structure also, C6H5, the phenyl group, so that it looks somewhat interesting to you. These triple bonds like that. And now I'm adding, this is our C6H5. This is my phenyl group. Okay, attached with, this is the bond with magnesium bromide. So what is the name? Name is a phenyl magnesium bromide, right? So this is the way you can show it like that, or you can show it like that. I'm just showing because I wanted to show you what actually happens. So this bond is between carbon. See, carbon is here and magnesium is here. Non-metal, metal bond. It is highly polar. So what will happen? The carbon, which is here, will take this bond onto this well. And if we take this electron, it will become negative. And what this will become? This will become positive. So instead of that, I can show, as we broke the bond in the case of cadmium and R or carbon, the similar thing will happen here. This will become positive and this will become negative. This carbon will become negative. And now the attack happens. So this guy negative will attack, it will go and attack this carbon. Okay, and it's trying to establish the bond here with this carbon, but it already have four bonds. So nitrogen will say, oh, that cannot happen, you can only have four. Let me take back my bond, okay, my electrons. It will pull up this entire bond onto itself. It will become negative. Oh, what will happen when it will become negative? Is there anything closer by who's positive? Yes, so it will get attached here. So it will be here. So that is how we are getting the result in the first step as CS3CH2. Carbon now is bonded with nitrogen with only double bonds. And here it has been attached, so ring will be attached here. So our phenyl group got attached here. And MgBr will get attached here. MgBr. Br, magnesium bromide is getting attached with the nitrogen. And now what I want to do is I just want to break that, like these bond. I don't want with the nitrogen, I want with the oxygen, and I will do our favorite process, which is hydrolysis. So I'm going to write it like that. Okay, so that we have space. So I'm going to do hydrolysis, H3O positive. That's how we show that it is happening in the acidic medium. So now what will happen? This bond is going to break, and it will get attached with the oxygen, CH2. Carbon double bond is broken with the nitrogen due to hydrolysis. Lysis has happened. Oxygen has come from the hydrolysis, and that way down we have phenyl group. I'm not able to show it here completely, but you got the idea. Yeah. So this is our ketone prepared in the slow motion, how this is happening. One side note about this reagent, the reagent which we have used is a very popular one, which is called Grignard. Grignard reagent. So this is a scientist name. So which we have used here is a C6H5 aryl group, or like if in this case a phenyl group we have attached with Mg, right, and Br. So what is this? This is a halogen, right? One of the halogen, and this is aryl group. This is one aryl group attached with magnesium, right? A metal. So this structure will be called a Grignard reagent. Generally, if we want to see, we can say Ar, aryl group attached with magnesium, and then we have a halogen. X I'm showing is a halogen. It can be chlorine also. That is also halogen. And this Ar I want to say aryl group. If it is an alkyl group like simple R, that is also will be called a Grignard reagent. For that, it will be like R, Mg, X. So it can happen like, a methyl group or a ethyl group is attached to Mg and with the halogen. So this will be the structures, common structures for a Grignard reagent. So we have used this reagent. We should know its name also. It's very popular, known reagent. So now the third reaction, the final preparation. Don't worry, this is the last one reaction, and focus on that. If you remember what we did the last reaction with, what was the substrate? In the case of aldehydes, it was Gatterman-Koch reaction, and that has substrate as a benzene we used. Same thing. So I'm going to prepare my ketone from benzene, and this is the benzene structure. This it will look like, and the reagent which I'm going to use is acyl chloride again. So I can have like aryl group attached with it or R group, alkyl group attached with it. Yeah, so I'm going to use again the acyl chloride, right? So remember the first reaction was also acyl chloride, but we have to understand what is the substrate and which reagent we are mixing, and that makes the difference. So this is a separate reaction we can say. And now what we are going to use here as a supporting agent which will help us is anhydrous. Anhydrous means An means not, hydrous means water, without water, right? That we can think of. Aluminium chloride. So in this reaction, this will work as a catalyst. And we will understand when we are doing in slow motion what catalyst does, how it gets involved in the reaction, and what happens after that reaction. What is its role? So that is, if you put focus on this video, on this reaction, you will understand the role of the catalyst which AlCl3 or aluminum chloride is doing. So simply saying what will be the output of this in a shortcut method, if you say direct reaction, if you say here, it will get attached. So this carbon, okay, it can be the other side, it can be aryl group or our alkyl group, and we have a double bond of oxygen. And here we have ketone ready. Both sides, if you see, there is aryl or alkyl, here it is aryl group. So that is why this carbon have both sides carbon, and that's why we will say it is a ketone. So we have prepared a ketone here. But now the fun parts become, what is the mechanism? Let's go there. So now let's see the mechanism. So we are talking about three things here. One is benzene here. So I'm showing you the pi bonds here also, like this. And then we have acyl chloride, and then we have AlCl3. So our story will start with our catalyst, anhydrous AlCl3. If you see the structure of it, the aluminium is bonded with 3 chlorine. You can clearly see AlCl3. Yeah. So if you ask aluminium what you want, it will say I have around me 6 electrons. So it is shared 3 electrons of it with chlorine 1 electron. So around that there are 6 electrons. So let's listen to this. It's saying I have 6 electrons, and every atom what it wants, its octet to be complete. As of now, the octet is incomplete. So there is a need of this catalyst. Its octet is incomplete. It wants one more pair so that it can become octet or 8. From where it can take, here it's a acyl chloride, right? So we have Cl here, C here, double bond O. and aryl group attached here. Forget about this as of now. So let's say it is somewhere here. But first they are talking, right? So the chlorine has three lone pairs. So it will say, okay, you need that. Let's create a bond. So it will give a lone pair to the aluminium. So what will happen? Let's see. Let's go down. Okay. So this will become Ar C double bond O, right? And because this chlorine has bonded with, this has given pair with aluminium. So this chlorine is now linked with this one. So this has gotten a lone pair. So this will become negative. And because chlorine has given its pair, it will become positive, right? It will become positive. So it has created one more bond with it. And now aluminium will say, okay, everything around me is now Cl, 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 and I have a negative charge. So as of now, this is the condition. So this is unstable. Okay, Cl positive is very unstable. So what will happen is that this it wants to get break from here. It will pull this electron which is shared with it and get separated, right? Get separated like that. Okay, so AlCl4, because now Cl is positive, it will take this electron and get satisfied. But now the problem is with this. Now only three bonds will be remaining with this ARC double bond O, right? So what will happen? Don't you worry. Oxygen has two lone pairs. So it will say, okay, let them go. Don't worry. I will give one more bond with carbon. Okay. So what will the structure of this? This will be our aryl group, carbon, triple bond with oxygen. And will it matter? This pair is gone. So oxygen will say, okay, I have become positive. And this is a very, very popular ion. This is called acylin. Acylin ion. Acylin ion. Okay, acylin ion. We say that. This is a very popular ion. And what happens? It has taken this chlorine has taken this lone pair with it. It got satisfied, but of course, aluminum still has negative charge. So we have AlCl4 negative. From the start, only AlCl3 and this acyl chloride have talked, and they have made this acylium ion. Now comes the attack. Let's see. So the third thing, our substrate now will come into the picture. Our substrate was our benzene. And I was telling you that I have shown here pi bonds because those are important here. So this carbon, okay, this carbon has to take some electrons. Okay, so it will take electron from this pi bond. Pi bonds are weak, so it will be broken and it will be going here. Now here is one confusion. You will think like, why it's not going directly to O positive, right? The oxygen wants electron. I agree, but understand oxygen is. I will side note here. Oxygen is still highly electronegative. That's its nature. Okay, so it will not still take the from the outside electron, right? So what it will do, it will take this pi electron from this benzene will be gone here, and then oxygen, due to its electronegativity, take this bond back. So now it got attached here. So our final figure will be like this. So it has attacked this with this pi bond. It broke this pi bond. This electron has gone and gone into the carbon. So it got attached here, okay, like that. And I will show one pi bond missing here. This is gone. So only this and this is remaining, right? And now carbon has double bond with oxygen. That's what we wanted, right? But still the picture is not complete. See this, we have AlCl4 here, which is having negative charge. Okay, and here if you see something is missing, right, it has to be stable. This is not the stable structure. If somehow the pi bond comes back here, it'll be stable again. So from where it can snatch the electron. So you understand this carbon. So this carbon is attached with this carbon, this carbon, this. But I am not shown here any positive negative. It means there is a bond which you don't show, which is hydrogen, right? Hydrogen is already here. Understand this step very carefully. So hydrogen is there, right? So this structure wants its pi bond back. So what it will do, it will break this hydrogen, and here it comes the pi bond back. And what will happen to this? This will donate H positive. So let me write AlCl4 carefully here. So this is what the AlCl4 negative charge here. Okay, so now what will happen here, it is H positive, which is kicked because we want stability here. So the H bond is broken. It has come as a pi bond, and this H will go with Cl. Cl will take this electron with it, so that aluminum will also get freed with this negative charge, and this will happen. And this is acid-base reaction. This is acid-base reaction. Yeah, so it has come back. The H is also gone. So now our structure will look like this. This double bond oxygen, and now have we have our benzene back with its pi bond, right? So this is a stable structure. What happened to this? See, HCl is gone, and again AlCl3 has come back. It is regenerated, right? So that is what the catalyst do. See how they played a role, but at last of the reaction, when everything was stable, everything is hunky-dory, they came back into the same form which they were.
So we have done three reactions. Now you will again be thinking like, how to remember all these. Please note that one time doing this will not help. As of now, just watch the video and note it down whatever I have said. And if you see the mechanisms which you are difficult to remember, there are two things. First thing is there are regions, different names, and there are substrates which are different, right? So what we need to do is discussion so that whatever we are discussing comes into our natural language. Then phenyl magnesium bromide will not be a fancy word for you. If you do it for once, of course, it will remain fancy for you and you will try to remember it. We just need to discuss it. Repeat this video again, write that again, try to write everything or what is coming beforehand and try to get ahead of the video next time. Second thing, a discussion with your friends. And third thing, very important, is to understand mechanism. That will give you a better idea how the reactions are happening. And slowly, when you do more and more reactions, you will your mind will get the pattern, like how it is happening. Same thing is happening with cadmium, then same thing is happening with magnesium also. Like that, you will be able to relate. So cramming that, whatever we have done, will not help ever. What we need to do, we need to view this. We need to write this again and again, and discuss it more, so that we are habitual of these kind of fancy words. And remember, the mechanisms are just a story. Somebody is attacking, somebody is leaving, just like that. Okay, so remember that if you do these things, of course, you will find it very, very easy to do it. But doing one time will not help. So best of luck. And now the next video will be of reactions. We'll be starting reactions. So let's see you in the next video. Thank you.